That should be working.
Whoa.
We'll need someone to confirm our existence as usual. Corvair Wynn asks, how angry does Jeff get every time Crew Dragon lifts off? How angry would Jeff be when Starship lifts off with his first test flight around Selene? I don't know. 7? I'm not sure how angry he gets. Okay, we did it. We should be live. How's everyone doing?
Good.
Good.
How are you, Fraser? Yours.
Good. I mean, the usual, like living in a temperate rainforest in a trailer, regular issues with a snow line that is creeping closer and closer to our altitude, our elevation. So,
are you not more settled than you were when I talked to you like a month ago?
Oh, we're more settled in that we have more of a shop built than we did a month ago. Yeah, no, we're not gonna be able to move into that until probably February or March. So we're gonna see the full.
You're gonna endure winter
of a Canadian winter living in a trailer.
Yeah.
Well, for what it's worth, it's trying to snow here.
Yeah.
In Colorado.
Yeah, I mean, we've definitely learned that we have probably double the rain that we had in the city down below.
Wow.
So it's just the rain is just off the charts, but we don't get as much wind, which is nice. So it's not actually that windy because we're sort of protected in all directions.
It's 70
by the
degrees
forest
here in
or
DC.
what? The geology?
70 degrees. Yeah, we're protected by mountains around us. Yeah, 70 in DC.
70 in DC,
my.
70 and sunny and gorgeous.
Oh,
Yeah,
wow.
It was only a little colder in New York.
Yeah.
That's
Had the windows
crazy.
open. It
Wow.
was great. Yeah.
In November.
In November.
Because you guys can get a lot
climate
colder.
Change.
You can get colder than we get.
Oh yeah. No, like
Yeah.
it's been like in the negative teens before. But
And that's in Fahrenheit.
yes.
Yeah, over
in
the
Fahrenheit.
weekend we had temperatures in the 60s and 70s here. We had the doors open and we're wearing T-shirts outside. It was pretty nice.
Yeah, no, I think
Nice and alarming.
Nice.
yeah, exactly. Yeah. Right, the climate apocalypse never felt so comfortable.
It's a great week for a climate conference.
We're
What are
gonna
you
get the
talking about?
T-shirts. Yeah.
Yeah, exactly. Someone saying the audio sync is off. I don't know if Pamela. There's nothing you can do about that. That's just like somewhere between server and the who knows.
Yeah, there's nothing.
All right. Well, I think
can
we're
do.
gonna get things. Yeah, I think we'll get things started then. Hello and welcome to the Weekly Space Hangout for Wednesday, November 10th, 2021. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about, finally, the 2020 Decadal Survey is out. And it's like a 600-page plus document. So we got a lot to talk about. Astronomers have released all the gravitational wave merger detections so far, and there are a lot, more than you thought. And yes, it's going to launch already, and we have the proof. James Webb's booster has been revealed. So we're getting closer and closer. Joining me this week on my screen, we've got Veronica Klimowicz. Veronica,
Hello,
how's it
guys.
going?
Very well here in Europe. Night as always.
Night as always, yeah. Yeah, but does daylight savings time make your life easier or harder when we shift out of daylight savings time?
As far as I remember, it's always 2 at night for me.
You're right. Right, okay, all right. That's not good. We got Dr. Kimberly Cartier. Kimberly.
Hey, Fraser. Happy podcast day. Happy decadal survey time.
Yeah. We have to talk about why it's 2020, and yet I look at my watch and it says 2021. So we'll get into that. And we got Carolyn Peterson. Carolyn.
Hey there. How's it going?
Space writer.
Yeah.
Good. All right. So before we get into this week's episode and special guest, I want to give a huge shout out and thank you to our good friends at the Weekly Space Hangout crew. They're friends, our fans. They are the ones who really call all the shots, and we just dance to whatever music they play. So if you want that kind of control, really at a molecular level of me and the co-hosts, you're going to want to join the Weekly Space Hangout crew. Go to wshcrew.space. They'll hook you up, give you all the information that you need to join this amazing community. All right. Let's get in with our special guest. We've got Dr. John Forbes. John, welcome to the Weekly Space Hangout.
Hello. Thanks for having me here.
All right, the question I always ask, who are you? What do you do?
So I'm an astrophysicist. I'm a postdoc, so a few years after my PhD. So I write papers and look for my next job. I study sort of a bit of everything, but mostly the formation and evolution of galaxies, formation of stars, a little bit planet formation, a little bit of everything. But
awesome. And we're going to get into the little bit of everything, but I would love to talk about the 3D printed nebulae that you guys worked on, because this is so cool. I mean, this ran through my feed, so I had no idea that Nancy had you lined up as our guest. So let's talk about that first, and then we'll get into the research portion. I actually want to talk about I know you work on brown dwarfs as well as star-forming galaxies and all that kind of stuff. So let's get into all that, but let's talk about the nebulae first.
Oh yeah, I mean these things are unbelievably cool. I happen to have a little mini museum here on my desk. Oh, sorry, I'm bad at knowing where the camera is. So this is probably not coming through, but I have like a little micro museum on my desk of these things. So it's a wonderful thing to show people.
So why don't you explain then what it is that you're holding? Because we also have a podcast audience. So
yes. Right. So I was holding a sort of plastic-looking sphere, about 8 centimeters in diameter, of some sort of. It looks like a giant marble, and that is a model of an object we call giant molecular clouds, which are the sites of star formation that exist in our galaxy and in basically every galaxy in the universe. Probably the most famous of which is Orion. We thought we would try to look at these things in a new way.
Now the one that you're holding, and I remember seeing this from the press release that you guys did.
Yeah.
It's not any specific nebula. It's just it's a simulation of a nebula rendered in 3-dimensional form.
That's right. Yeah. So distances is like the hardest thing in astronomy. It's very hard to know exactly how far away things are. And the gas in giant molecular clouds is no exception. It's sort of hard to know like what the real 3D structure of the cloud is. Although I should say there's actually been like incredible progress on that recently because of Gaia. But yeah, so these are simulations which sort of my bread and butter. It's why I got involved in this project, and it's one of the most powerful tools we have as astronomers for trying to understand the physics of the various things we see out there in the universe.
So what do the different colors in the globe sort of relate to?
Yeah, so this particular example is made of two different materials. One is transparent and one is clear, and they're 3D printed. So they're sort of layered they're constructed one layer at a time, and then an ultraviolet light is passed over them to link together the two different materials. And what it represents is the density field in the simulation. So basically, in the simulation, we have a three-dimensional box that we've divided into 512 different cells along each edge. So that's about a quarter of a billion computational elements. And in each cell...
Wait, hold on. I screwed up.
Have a magnetic field. I feel like maybe I'm forgetting something. No, that's, you might also have a temperature if you care about that sort of thing in your simulation. Because we're studying molecular clouds in this case, we're approximating them as having a constant temperature. And so what the colors here are showing you is just the density field. So the more opaque the material in the sphere, the denser the gas is at that point in the simulation.
And how big of a space are we looking at? Like, how much universe are you holding in your hand?
Well, formally, these are these are sort of scale invariant simulations. You don't need to assign a particular scale to them, but you should probably so that's like the real technical answer. But the more useful answer is probably sort of 10 parsecs, or about 30 light years.
Right. Okay.
Is sort of the typical size of the objects we're thinking about here.
And so then, how many stars would probably come out of this ball of gas and dust?
Yeah, so that gets back to sort of the scale invariant thing. Like, we can sort of scale it up or down a bit. Giant molecular clouds in the local universe, that actually form a sort of healthy population of stars, like Orion. Orion has a few component molecular clouds, and they're of order 100,000 times the mass of the sun. Not all of that is likely to form stars, but a good chunk of it. So we're talking sort of 10,000 solar masses, which translates into a few times 10,000 stars, individual stars.
Wow. So in that, like, a 30 light year diameter sphere, you would have tens of thousands of stars forming all at the same time.
Yeah, that's right. Like, this is, so I mean, the background here is that these are, the reason these are the places where stars form is because they're sort of where the universe creates cold, dense gas, and that's what you need for stars to form. Like, usually, if you're an atom sitting in the middle of the galaxy, you're sort of lonely. Your nearest neighbor is more than a centimeter away on average, and you're constantly being bombarded with ultraviolet light and shock waves, and it's hard to sort of settle down into a nice cloud and collapse into a star. But in these molecular clouds, enough gas has gotten together by sort of large-scale processes in the galaxy that it's able to sort of protect itself from the ultraviolet light of other stars. And so, the gas that we're modeling here is sort of 1 million times, roughly, denser than sort of the typical gas in the galaxy, and about 1,000 times colder. So it's only a few degrees above absolute zero, and that's like the perfect environment to form stars. And they also happen to be extremely messy, turbulent places, and that's why these simulations, which are sort of an idealized case of an isothermal, i.e., constant temperature gas, being driven by turbulent forcing, are a good sort of toy model for what giant molecular clouds actually behave like.
So, I know that the thinking about how star formation, like what triggers star formation, has been evolving over the last couple of years. Like for the longest time, the story was you had this giant cold cloud of gas and it wouldn't collapse on its own. You needed some kind of kick, like a supernova exploding nearby. Where are we at now in sort of what is the modern thinking about what it takes to actually start triggering star formation in some region?
Well, I mean, you certainly do see examples in the nearby universe where it certainly looks a lot like the story you just said, where you have, one of these giant molecular clouds sitting next to a region where like there was just an explosion right here, and it looks like, oh, maybe something exploded here and condensed this, and that's what's causing this set of star formation here. But it's not. I think it's fair to say the consensus now is none of that's really necessary. Like you can, like, a giant molecular cloud is wildly unstable on its own, and if you just sort of put in the conditions for a giant molecular cloud, like in these simulations, and turn on gravity, it will collapse right away. And the real problem in star formation is how to prevent all of it from collapsing immediately and forming stars. So we sort of have the opposite problem, I would say.
Right. So you're saying like what you can't figure out is why all the cold gas in the universe hasn't already just turned into a bunch of stars.
Yeah. I mean, we have some pretty good ideas, but the details are very complicated because they involve the explosions of stars, they involve radiative transfer, they maybe involve magnetic fields, and maybe involve cosmic rays. So we don't know exactly what's going on, but we do know that, yeah, if you didn't have anything sort of pushing back against gravity, then you would form stars way too fast, and we don't see that in the real world.
Now we know that the universe star formation anyway, is kind of winding down. We missed the big party, which was several billion years ago. If we could transport back to an earlier time in the universe, sort of the most active time in star formation, what would the Milky Way look like?
Do you mean? Well, that's a very interesting question. Do you mean like?
I mean, either from
the
like
thing that
from
became the Milky Way, or?
Sure, yeah, I guess so. Yeah.
Yeah. So of course the Milky Way is also growing during this time. So
yeah, the most successful dwarf galaxy in the region.
Yeah. Yeah, I mean, so galaxies sort of that are like the Milky Way now, in terms of their mass, at redshift 2, i.e. 10 billion years ago, when the big party, as you say, was happening. Some people call it cosmic noon, because that's where the highest density of star formation in the universe was taking place. Those galaxies tended to be much more gas rich. So our favorite way to quantify this is the gas fraction, so sort of the ratio of gas to stars in a galaxy. For the Milky Way, the Milky Way is sort of a retiring galaxy. It's 90% stars, 10% gas, something like that. But for a galaxy at cosmic noon, it was maybe 50% gas. So so really, like, the stars are at redshift 2, like the stars are kind of an afterthought. They're like, what's really going on is all the gas dynamics.
And then one of the other questions that I have is where are we at with the first stars, the population 3 stars? I mean, I guess that's it. Where are we at with them?
Well, I mean, that's an interesting field because it's very tough to get observational constraints on the first generation of stars. So a lot of that work is extremely simulation heavy, and every once in a while they're like, oh, we realized that this molecule that we hadn't added to our reaction network is actually kind of important and changes the picture a bit. But I think the general view is that population 3 stars are probably a substantial amount more massive than the stars that you typically form nowadays, just because they don't have metals, so they can't cool. And so, yeah, so the game in population 3 star formation is sort of understanding all those cooling processes and the very, very high redshift universe, where now you have to worry about, like, you know, which teeny tiny dark matter halo, which is like a million times smaller than the Milky, or even more than a million, yeah, a million times smaller than the Milky Way's current dark matter halo. Like, what are they doing with respect to the gas? So yeah, it's a tough business, and I think everyone's hopeful that James Webb will literally shed some light on that.
Oh, and we're going to talk about the decadal survey, because I think it's going to be probably the Origins telescope is the one that'll, like, James Webb hopefully will get to the first galaxies coming together, but it'll take Origins to actually see the first stars, or the
could be.
Yeah. But it's I mean, it's such an interesting question to me. Like I love the fact that when it comes to these biggest stars, you ask an astronomer, like, how big could they have been, and they're like somewhere between the size of a star and 50,000 times the mass of a star. I don't know.
Yeah, this is what happens. This is what happens when you don't have the photons to tell you the answer. Like,
yeah. And exactly
astronomy is really, really driven by the telescopes, and the theory is sort of like we're trying to catch up and piece together what's really happening.
And it's interesting that as you just said, you just figure out, like, just the way the chemistry of one molecule works, and like suddenly you're like, nope, okay, then they had to be small. Oh no, wait, they could be big. They could have been massive. Yeah, and yet those were the building blocks of the entire universe. They lived, died, put out the heavier metals, and everything is sort of a chain of events coming from that. And it's got to be tough to. We have the later stages of this chain of records, but we don't have the earliest stages yet.
It's true, but I mean, I think it's also fair to say that we don't understand the late stages very well either.
Great. So we don't understand anything. Okay.
Yeah, I mean, even what we're showing on the screen right now is a beautiful image of the Orion molecular cloud, which is the nearest massive region of massive star formation, and we're still learning new things about it, because we only recently got really nice distances to a ton of the stars in there, and so we're trying to really understand these regions at a level that just was not possible before, because we didn't have the data, and yeah, and I guess, right. Sorry, I'm like trying to see what's actually on the screen here. Yeah, so I mean, one thing I wanted to mention about this region, which is so cool, is people think Orion and they think, oh, it's the constellation, and it is, but it turns out that about the same size as the constellation on the sky is also these giant molecular clouds, which are like our keystone for understanding all of star formation and all of the universe. And it's because we're trying to understand this one example that happens to be very close to us as well as we possibly can.
Yeah, that one image on the left is showing like the full Orion complex, and really just showing the entire Orion constellation, and showing all the nebulosity that's in there. And that whoever took that image is a master, because it's such a big piece of the sky, and it's such a pain to calibrate as you take each frame to try and get the images to be roughly looking the same. Those kinds of giant scale mosaics are I have so much respect. I take one picture and I'm like, ooh, I did it. Right. To try and stitch two pictures together, it just becomes more and more difficult. So yeah, hats off to whoever pieced that entire monster together. Well, we're out of time for the interview portion. But John, if now, is there any way that people can like buy these 3D printed nebula to support your science? You've got like some kind of gift shop rolling yet?
Oh yeah, it's a common question. I mean, if you really, really want one, it would be probably a few $100s. We're not looking to like turn a profit on these. It's just how much it costs to make the materials. And before we move on, I did want to at least mention, you know, I'm the face of this project tonight, but this, you know, this work was not led by me. It was led by Nia Imara at UC Santa Cruz, and we also collaborated with James Weaver at Harvard, who is our 3D printing expert. So I really wanted to like emphasize that, you know, this is a team sport, and I'm just sort of the simulation guy who had a lot of fun.
Well, I wish there was more of that. I mean, just this idea of these people of different skill sets coming together to help illustrate something that can be a little difficult to imagine, to be able to provide this kind of a 3D printed version of it, I think is really wonderful. So congratulations on that collaboration. Awesome. All right. Thanks, John. And let me know when you have your store online, and we'll point people towards you.
Okay.
All right. Thanks a lot.
Thank you.
All right, let's get on with the news portion of this week's episode. All right, Veronica, you're first on my screen, so let us know what's going on with James Webb.
So, yeah, it's coming. But I would talk a little bit more about like what will bring James Webb to where it's supposed to be. But yeah, so that will be our largest and most powerful telescope ever launched to space. And as a part of international collaboration, ESA was providing telescopes launch services using Ariane 5 launch vehicle. And working with other partners, ESA was also responsible for the development and qualification of the Ariane 5 adaptations for the Webb mission, and the procurement of the launch services by Ariane Space. So what's happening this week, basically, is that Ariane 5 core stage was taken out of its shipping container and raised vertical, and it was happening on 6th of November. And basically, these activities mark the beginning of the 5-week campaign to prepare the Ariane 5 launch vehicle, which will run in parallel with the teams preparing Webb, which started already 3 weeks earlier. So, and in around 3 weeks' time, the Webb would be placed on the Ariane 5 in the launch vehicle integration building in European spaceport, French Guiana. I hope I pronounced right. Mm-hmm. So the Ariane core stage is 5.4 meters in diameter and 30.5 meters high, which is a little bit more than a half of the size of SLS core stage. And at launch, it will contain 175 tons of liquid oxygen and liquid hydrogen propellant. And with its Vulcan 2 engines, it will provide 140 tons of thrust. And it will also provide the roll control during the main propulsion phase. And this roll-in maneuver will basically ensure that all parts of the payload are exposed to the sun equally, and there will be no overheating of any parts of Webb. So this week, 2 boosters would be placed on the vehicle installation table and anchored to the core stage. You see the core stage right now on the screen. And the boosters, they are 3 meters in diameter and 31 meters high, almost as high as the core stage itself. So the engineers will then start carrying various mechanical and electrical checks. And each of these boosters that will be added basically this week will contain 240 tons of solid propellant, which will basically provide the thrust needed for the lift off, hopefully in around 5 weeks' time.
Wow. So before we go, apparently the chat is saying there's like a loud typing noise, and I'm not hearing it at all. So my guess is that Pamela is typing, and it is somehow broadcasting only to the video feed, but not to the Hangout that we're having here. So Pamela, if you're listening to this, if that's true, you might want to mute your typing. You have a very fancy mechanical keyboard. So how much dust do they have to blow off of the core stage to in getting this set up? I'm trying to think,
So
how long has that core stage been waiting for this job?
they just basically placed it, and it will take another 30 days to.
But when did they build it? Like they've Arianespace has moved on to the Ariane 6.
Yeah. So the
They had
Ariane,
to take this one out of a museum, right, to
yeah,
help
right.
launch James
The
Webb.
Ariane 5 basically finished like around, like, I don't know, 100 launches already before that, and they had basically to adopt it to this one. And yeah, there is already the Ariane 6 working and like lifting stuff in space. And actually, I'm not sure how long it had to wait. Maybe you, Fraser, know.
No, I don't. I don't know. Yeah, I actually don't know how long, but I do know that this rocket has been
it was,
waiting for this task for
I
quite a
think,
while.
like let me check Wikipedia. I think something like 2017. they basically finished like launches with the Ariane 5, and like how many years is that now? 5, 4?
Yeah.
Yeah.
And we saw the upper stage about a month ago show up. It left Europe about a month ago, and so it showed up. And of course, we just saw the unboxing video of James Webb. So, and then it's going to have some solid rocket boosters. Is that right? It's going to have some side boosters as well.
Solid
Yeah, it's a
rocket,
heavy lift.
yeah, solid rocket boosters, right? There's 2 boosters that I was talking about that would be placed basically this week, and then it's just the engine on the core stage as well. So it's just 2
And as you
stages.
said, it's about half the lift capacity of SLS. Is that right?
Yeah, I mean, no, it's half of the size. SLS
Oh, okay.
has much more lift capacity. So
Okay,
I think like Ariane 5 is having like 6 tons of like payload, and SLS is having I don't know, so much more, like 5 times more.
Yeah. Yeah, this is going to be, it's a monster payload. I mean, James Webb is gigantic, and it's going to take a lot to get this thing off the ground. So
Yeah, I feel like the pictures on the screen, it's like size of the tennis court, right? So it's also very, like, I'm sure you've discussed it in previous shows, but like this folding and unfolding would be absolutely interesting to see. And we would actually know whether whether everything is working like in 6 months' time after it launches. So
someone mentioned something kind of terrifying to me on, I think it was on Twitter or something like that, where we saw that Lucy, one of Lucy's 2 mechanisms designed to unfold malfunctioned. So that's a 50% failure rate on a folding mechanism, and James Webb has like 100 and plus.
yeah, I was trying to read the sequence. I'm like, oh my god, like
yeah,
they are very
it goes on for 30 days.
Good engineering.
And it's just yeah. Kimberly, did you see that we actually used your title? And in fact, NASA did too.
When? Let me see. What was it? What did I say?
It was, you said the 30 Days of Terror for James Webb.
Right.
Yeah, so Nancy Atkinson wrote that up as a story on Universe Today. And then like a day after, NASA released a video which was their 29 days of, I forget exactly what they called it, but essentially, so you're exactly on the right track with getting that concept across. Yeah, it was awesome. But it was really fortunate because
I will be terrified for those 29 days.
I know. Nancy had actually interviewed a whole bunch of the people involved, and she had a whole bunch of quotes and stuff from the different people that she was able to pull into this one article. So yeah, if you haven't got a chance, definitely check out Nancy's piece on this 30 Days of Terror for James Webb. But yeah, it's just going to be day after day after day of us watching every single piece unfold, every actuator and sun shield, and Anyway, all right, let's move on. But thanks, Veronica. All right, Kimberly, the Decadal
Hey,
Survey
the
2020.
Decadal Survey. It arrived. It arrived last Thursday, November 4th, in a 600 plus page document that I read cover to cover in a day so that you don't have to.
Did you
I did. Yes.
really?
I did. Yeah.
How was it?
Dry. And sorry, it is very technical, but there were a lot of interesting tidbits in there. But at the start of the show, you had asked, why is it called Astro 2020? And yet it is released in November 2021. The Decadal Survey process, just to back up a little bit, is a multi-year process that takes hundreds, if not thousands, of people to actually complete. This particular Decadal Survey process started in November 2018, which is 3 years ago. If anyone can remember back to 2018, what was going on? Basically, immediately after the first steering committees were chosen for the Decadal Survey, the U.S. went into a 35-day government shutdown, which meant that no one at a government agency could work, like NASA. So that was a setback. And then this thing called a pandemic happened, right as the larger committees of like 150 people were supposed to be meeting March 2019. And then towards the end of 2019, and then at the beginning of 2020, they were supposed to be meeting to make a bunch of decisions. And we all know how March 2020 went for everybody.
Yeah, I believe that was a dumpster fire.
That was a particular time. And so the report, which was originally scheduled to be released sort of in the summer of 2020, was pushed back to the spring of 2021. But then, of course, the pandemic did not end in the spring of 2021. And so we have this report now in November. And it was definitely worth the wait, I think. I have only personally seen 3 decadal surveys in my lifetime, but I think this one is, of my opinion and other astronomers' opinions, is probably one of the most well put together and doable decadal surveys that we've seen in a while. And that's mostly because there is no giant flagship telescope that has been put forth as the top priority. A space telescope, I should say.
Not LUVOIR? I mean,
LUVOIR was not put forward. The actual large ultraviolet infrared surveyor, optical surveyor. LUVOIR, the actual telescope proposal, whose name is LUVOIR, was not put forward as a recommendation. Neither was HABEX, the Habitable Exoplanet Observatory. Instead, what the top line recommendation is actually for a Great Observatories maturation program to develop an idea that's sort of they requested a hybrid basically between what was proposed for LUVOIR, what was proposed for HABEX, sort of a 6-meter size space telescope, so still pretty big, that is specifically designed for studying habitable worlds. And none of the 4 great observatories that were proposed for this decadal survey really fit the bill for what the committees wanted. And so they said, take more time, develop this concept to meet this particular science goal, which is trying to find the first signs of life on a habitable planet. And so it's actually, in my opinion, a very good move, given what we know of the incredible setbacks that James Webb has experienced, and the Nancy Grace Roman telescope, which is also not yet launched, but is technically the next flagship, has also experienced.
But it's gone like clockwork. Like the delays have come from politics, not from the technical issues with Nancy Grace.
This is true, but you do have to consider those sorts of things when you're trying to build a many billions dollar, decade-long telescope program. And so this Great Observatories Maturation Program is sort of what they're calling a new paradigm for approaching these very large missions, because James Webb, encountered so much difficulty, and for so long that it has pushed back so many other programs that have been proposed and accepted for more than a decade now. It's a way to approach larger programs like this in a more strategic way, and to give them more security in developing these very large missions.
So is the idea to roll out some of the new technical risk into stages and steps in different missions, so that you're not sort of jumbling up all these technical risks into one big mega mission?
Yeah, it's very much a technical development program that they're trying to literally get off the ground. And part of it is going to be also developing, like you said, these technologies into smaller telescopes, into smaller programs that will launch and were proposed in this decadal survey, just not immediately part of a brand new flagship when there are still 2 flagship telescopes that have not yet launched.
Right.
And some of those telescopes are, we mentioned earlier the Origins Space Telescope, and there's also the Lynx Space Telescope, both of which, one is an X-ray telescope, one is a far infrared telescope. Both of those were recommended for development. There's LISA, the Space-Based Gravitational Wave Observatory, which was recommended. There's a Cosmic Microwave Background Observatory. There's IceCube, which is on the ground, but doing cosmic ray things. And all of these are opportunities for technological development that can lead to not the next and not the next, but the third next flagship that will hopefully launch.
Were there something surprising in this survey for you?
I mean, for me, I think the fact that there wasn't another flagship that was proposed is indeed a surprise. That's a big departure from past decadal surveys. And the fact they didn't even pick any particular telescope at all and say like, oh yeah, we could do LUVOIR, but like 20 years from now. They said, no, we're not doing LUVOIR. We're not doing HABEX. You're going to give us something new. You're going to give us something totally different. I was also a bit surprised at the very heavy science emphasis on the search for life. It's sort of it's interwoven throughout almost the entire report, including the parts that were really about like the evolution of galaxy formation and star formation. Also had very heavy hints of the search for life and astrobiology in there, and I think that really reflects what they're hoping to get out of James Webb, and sort of what the public and also what Congress has sort of been pushing for.
Right. I had a chance to interview the director of NASA's astrobiology group about a week ago, and you could really feel that the winds have shifted from we don't search for life to we search for life.
Yeah,
like, that's where we are now. Is that?
And
I
think
no
they're still
longer
very
the
particular about saying
science.
search for life, but not saying search for extraterrestrial intelligence. They're
Yeah.
still being very careful about the fact that this is astrobiology, so searching for, microbes and bacteria and plant life that leave signals in the atmospheres of exoplanets. That's something that James Webb is not actually designed to do. It doesn't reach the far infrared that will really help do that, where all these biosignatures really tend to stand out.
Yeah.
But that's really what they want. Whatever this LUVEX, whatever we're calling the
LUVEX.
That's
LUVEX links gins.
Like,
yeah.
It's a hybrid.
Yeah.
Between all of these things.
Yeah. Carolyn, what have you been following some of the releases from the decadal survey?
Yeah, actually, and what really surprised me was the day that came out, suddenly I got this swarm of press releases from all the giant ground-based telescope people and the radio telescope people. And so it seemed like there was a little something for everybody. There was much rejoicing happening.
Yes, I haven't even touched on the ground-based stuff. You're absolutely right, Carolyn.
Yeah.
Because there was actually a very large section of the report that was all about let's do the next big ground-based US observatories. And particularly, they want something to compete with the European Extremely Large Telescope. They want a US version. They didn't really care whether it was the Giant Magellan Telescope or the 30-meter telescope or both. They said, do a significant
they're all jumping
investment.
up and down, right? Yeah, and they're all
do
jumping up and down about it.
Investment
Yes, it's
on
awesome.
one of these or both of these, but make a decision by 2023 and then drop the other one. You're going to pick one and do it. There was also a next generation very large baseline array to replace the current VLA and was it VLBA? Yeah.
Yeah, I think they're going up to 263 telescopes across all of North America, mainly in the US, but there will be telescopes in Canada and Mexico, and it will essentially provide a competition to the Square Kilometer Array. A northern hemisphere giant telescope that is acting like a telescope the size of the northwestern hemisphere. Amazing.
Yeah, absolutely. Yeah. And so unlike the space telescope component of the report, the ground-based section of the report was very firm in saying, we want these two things. Give us a big array, give us a giant telescope. And the space-based ones are sort of TBD.
And it feels like with, say, the Event Horizon Telescope and with all of the pathfinding that's being done with Meerkat and what's being done in Australia, there isn't a lot of technical risk. Build more dishes, link them all up.
Yeah, that's something, though, that we've gotten very good at doing. Many countries, many observatories have gotten very good at doing that. And the U.S. astronomy community is saying, let's get in on that.
Now, I didn't hear anything about any kind of planetary exploration yet. That comes later, right?
That does come later. There was a part of the report that says we recommend doing at least one probe class mission a decade. So those would be the sort of things that would be planetary explorers or the smaller telescopes that could do very specific and narrow band astronomy, like in a very specific narrow wavelength range. Those are still sort of TBD, but they said, give us one a decade.
Right. Very cool. All right.
Lots of things in there.
Yeah. 600 plus pages. It's sitting on my laptop. I haven't, I downloaded it and I'm just like,
it's okay. It's very long. You don't really have to go through it if you don't want to.
But there's going to be lots of like little nuggets, is really interesting. So no, I will go through it at some point. All right. Thanks, Kimberly. All right, Carolyn, what have you got for us?
Yeah, I do want to add something to what Kimberly said, and that the radio astronomy community was ready to bounce. They've had these arrays on the drawing board for a long time.
Yeah.
So, I think it was like they're just waiting. And 1 second after that survey came out, they're pushing send on the press releases. It was pretty good. And I'm really pleased about it, too.
Yeah, it's funny. I got press releases. You're exactly right. We got press releases from the National Radio Observatory and from the GMT people that day.
And then I had personal emails from people who work at both of them. So it was like, did you see the news?
Yeah, same thing.
Well, Fraser, this is what happens when you don't get your embargoed material.
Right.
Yeah.
I was reading the report a day before it came out.
Right. You had a whole day ahead of me. Yeah.
Oh, there's lots of whispers going on. Yeah.
Yeah.
Well, also last week, then we had this press release. Actually, there was an archive paper that came out about 35 new gravitational wave detections that were about to be announced. And then then I started seeing stories everywhere about new gravitational waves being announced. And this is all done by this international consortium of LIGO, Virgo, and the CAGRA. So LIGO is in the United States, Virgo is in Italy, and CAGRA is in Japan as part of at Kamioka. And these are three basically observatories out of several that in the world that are basically looking for these gravitational waves. And I thought this was pretty cool. So, you see here three of them. So CAGRA's in the upper left, Virgo's in the right, and then the two below are the LIGO installations, one in Hanford, Washington, and the other one's in Livingston, Louisiana. So basically spread out across the world, they're catching these little tiny squiggles of gravitational waves. And they've been updating this catalog of gravitational wave detections all along. And last year they had a bunch, and then they added 35 more this year. And now we're up to 90. And so I'm reading this story, and I'm thinking, there's a million little things that you could get out of this story, but there were three things that really jumped out at me. And the first one was, we've gone in 6 years from one gravitational wave detection in 2016 to 90 announced today, which is really cool. I mean, it's almost like this time dilation effect. We've just gone from 0 to 60 in no time whatsoever. And all of a sudden, where we used to have Einstein telling us, well, it's theoretical, but we'll never find them, to, oh, we've got 90 already, and we're going to find more. So I thought that was pretty cool. And I remember the very first one, the black hole with the signal, they're putting out this great picture of these two black holes colliding, and there's a little signal, and they basically called that the chirp. And so that was a pretty cool thing and excited everybody's attention. But what does it really mean? And basically, aside from the fact that it's telling us that these massive things out in the universe are colliding, now we've got to figure. They think it was two black holes. One was about 26 solar masses, the other one about 36 and 29 solar masses. They collided and they send out this gravitational wave. Well, now with 90, they can start characterizing more and more and more of what these objects are that are colliding. So most of them are black holes. And one of the headlines that I saw basically said that they've seen black holes of all shapes and sizes colliding now because they have a big enough population to look at them. And the biggest growth in these of the numbers of black holes that they're seeing are in these intermediate class or intermediate mass black holes that I think back when I was in graduate school, those were still kind of theoretical. They weren't sure that they actually existed, or they weren't that many of them. You had the supermassive.
Theoretical. Like
yeah,
even
but
now.
They're saying now we see. They're saying now we think there are these intermediate mass up to 100 solar masses or something like that. Yeah. So you have these black holes colliding. They're creating these, so they can now characterize masses of black holes. They can go back and try and figure out what the pre-merger masses were, and even before that, what was it that formed the black holes in the first place. And what we're basically doing is probing what they call the stellar graveyard of these massive things that used to be massive stars, and now they're these, neutron stars and black holes, and they're out there colliding. And it kind of gave me this mental image of skaters at a skating rink. They're all running into each other. So I thought that was pretty cool. We had the stellar graveyard. We're probing that. But there's also, basically looking at stellar evolution. This is giving you some information about that. But cosmologically, there's also some implications about what we're getting out of these gravitational collisions. And in particular, they're looking at gravitational waves as a way to probe something about dark energy and the expansion of the universe and the history of the universe. And so several years ago, when they were first talking about this, we have one or two collisions, we can kind of make some guesses. Now we have 90. We have this really big population of these, and we can now make some guesses, some very educated guesses about what the expansion rate of the universe is and what role dark energy is playing in it. And the very bad pun was, we're shedding light on dark energy.
Well, one of the handy side effects of a black hole merger is that you get a standard candle out of it.
Yeah, absolutely. Yeah.
And so the distance of where this collision happened, and the more of them that you get, the more information you get from this. And go ahead. Oh, I was going to say, and then when you get the kilonova, like when you get the neutron stars colliding with each other, not only do you get that standard candle, the distance, you also see the radiation, and so now you can double check your radiation.
Yeah, you can compare and contrast. Yeah.
So they're on track to answer a multitude of questions about cosmology.
Yeah, and I think one of the things that I found really interesting is that one of the guys that they interviewed was saying basically there are questions we're not even sure how to ask yet that we're trying to find out, and I thought that was really cool.
Yeah,
that, these little tiny wiggles, these little tiny chirps that have been so difficult to detect suddenly can tell us a whole lot more. There's, black hole implications, there's cosmological implications, and there's just the fact that this is happening, that we've now got 90, and how many more are we going to have in another year when they bring other detectors online?
Carolyn, I have a question. They announced 90 of these at the same time, which is just it's kind of mind-boggling. How in what time span did they detect these 90 gravitational wave signals?
Well, it's 90 total. They They actually announced 35 more, and that was 35 since the last catalog update, and I believe it was 2020.
And this is over the
still,
course
like,
of 3 runs. So
3 runs.
They had LIGO, and then they had advanced LIGO, and then I forget the super duper advanced LIGO. So the latest one with I think they detected none with the first run, a few with the second run, and then like pretty much one a week with the third run. And
yeah, it's almost like suddenly, they were all there and we just never saw them before, and now we're catching them. Once they got the technology down, they were able to start really finding them.
Yeah, and that's exactly it. Is that each time in between the runs, they sort of take the whole system apart and come up with these incremental improvements at every stage of the system. So they had a more powerful laser. They used a technique called quantum squeezing, which is just so cool, because you essentially sacrifice, and I forget which it is, but essentially, you've got the uncertainty, you've got the uncertainty principle, and you can tell you the motion and the position or the position and one, but not the other. And so you can essentially force one of these, lose data on the other side, but it doesn't matter for these gravitational wave detections. And it allowed them to get a substantial increase, plus adding the new detector. And so there's this wonderful, and now the whole system is apart again right now while they're fine-tuning and improving it again. And so we should see another scale up in magnitude when the next run happens.
Yeah, I mean, every time that they do a run, they learn more about, we should have done this, we need to tweak that. I was up there after the last AAS meeting that I went to. We went to Hanford on a press tour, and they were basically saying, we start a run and we start learning all these things, and we're making, notes as crazy fast as possible to be able to figure out what we're going to do in the next improvement cycle, which comes way too fast.
And I feel like that really comes back around to what Kimberly was saying about ground-based observatories being a important part of this science moving forward. Like, you can't do that with James Webb. You can't do that with TESS. You're stuck with the telescope that you launched, but with the ground-based stuff, you take it apart.
And they make it look so easy too. I mean, I just think about how well they have to calibrate that system, and how well they need to tweak their software and their coding, and they just make it look so easy when they do it.
But do all three? Oh, sorry.
Oh, go ahead, Veronica.
Do all three should confirm that some gravitational wave was detected, or is it like if any of them detected, then it's fine, then it counts?
No, well, in this case, they have been working together. I don't know the details of how many of each observation all three of them did. For example, the very first one was LIGO and Virgo. And then they added in CAGRA, and CAGRA, I think, is also down for regrooving at this point. But I once one hits, say, did you catch anything? Like a neutrino detection or something.
3 gives you direction.
Yeah, it does.
When there was only the 2 of LIGO, you could just find out the hemisphere. So it either came from to the right or to the left. With the addition of the Virgo detector and the CAGRA detector, you get incredibly precise pinpoint.
You're triangulating
of where these things are. Exactly, you're triangulating. In fact, that's how they knew where the kilonova event happened, was because they had this array of telescopes, and that they were able to use that to target where to point the optical telescopes when they made the detection. And so now it's about expanding the sphere of detection to more and more, just a larger volume of space. So the next iteration is expected to increase an 8-fold volume of space.
Yeah, and they want to reach farther and farther out too. And of course, it really, you're kind of dependent on when the universe throws one at you, but you're absolutely right. They're expanding that.
What will LISA add to that in terms of directionality or precision?
So LISA, the difference between LISA is it's a much larger baseline. So in the LIGO detectors, you've got these 10-kilometer arms that are bouncing the laser signals back and forth. LISA is going to be 3 satellites with 10,000 kilometer long arms for this interferometer. And
it's a huge eye, basically.
Yeah, and because you've got 3, it's going to be able to detect it's going to give you direction as well. And so it's expected to detect merging supermassive black holes, merging white dwarfs, possibly merging white dwarfs with large stars, supernova that are like off kilter. So if you've got like I forget what it's called, what the term is, but if it's unbalanced supernova, and the real dream, it looks like they're actually starting to get this with pulsar timing arrays, is the background gravitational wave of the universe. So there is this ongoing ripple of gravitational waves. And I just did an interview with someone on this, so it's sort of all fresh in my brain. But essentially, if you've got two neutron stars orbiting around each other and they collide, you're going to get gravitational waves that are coming out of them that are many times a second. Like say you're going to get a few hundred a second of these waves before they collide together. With merging supermassive black holes, you're going to have gravitational waves that are light years long. And so you've got these pulsars, these vast network of pulsars out in space, and they're slowly drifting towards you and then drifting away from you as these giant gravitational waves are rolling over them through the ocean of the cosmos. And
I've kind of wondered how well that Lisa's going to give us the detail of those last few minutes to, however long it takes before they merge. There's got to be some really fascinating detail in that last moment,
Yeah, so these big supermassive black holes that are just slowly wheeling around each other, they're the ones that are creating this background waves. It's when they actually come in together and do that final spin around each other, that's what Lisa's going to be able to detect. And so you're going to finally get this full combination from LIGO, Virgo, Kagra, getting the stellar mass black holes colliding and the really extreme events, the very fast events. Lisa will catch the slower events, and the pulsars will catch the slowest events. And there's like one more, which is the actual, essentially the inflation of the universe, which is going to take one more observatory, a sort of a super Lisa, to be able to see that.
Yeah.
Okay, I'm going to coin another phrase right now. If they called the first gravitational wave like a chirp, they're going to call this longer one the heartbeat of the universe.
Oh,
somebody will, I'm sure. Yeah.
Fraser will, because I told him to.
There you go. Yeah, hold on.
Copyright that.
We're going to write this article right now.
First.
Yeah. I'll assign that one to Paul. He'll work on it.
There you go.
All right. Well, we've reached the end of our hour plus. We just got stuck in the poetry of gravitational waves there by the end there. So, Veronica, you're on my screen again. You get to shamelessly self-promote whatever it is that you're working on and tell people how they can find out more.
We are working with our new space community again, and we are organizing some, in collaboration with some unique guys, some meetup events online as well, just like to tell more about like Germany's new space. So if you guys interested, go to the meetup, space brewery events. They're happening very regularly, so join.
And of course, you mention these all the time on your Twitter feed, which is at...
I actually don't mention it, but I would now. Definitely, I would mention it. It's Veronica Space.
Perfect. Kimberly, what are you working on?
Oh, well, I'm coming out of my Astro 2020 fugue state.
But that document's gonna vomit stories for a decade.
I'm actually working on a story about the very early Earth and all the continuing efforts to solve the faint young sun problem. And so I've been talking to lots of paleoclimatologists and helioseismologists and all these wonderful scientists who are trying to collaborate to solve this problem. That probably won't be out for a little while, but until then, I'm on Twitter at AstroKimCartier. And all my stuff is on eos.org.
Fantastic. Carolyn.
So I'm thespacewriter.com and I'm at @spacewriter. And probably for the foreseeable future, I'm going to be digging into two topics. One of them is a book on solar system topics. And the other one is I'm going to dig some more into these gravitational waves because I just, those caught my attention like exoplanets did last year. So that's what I'm working on.
Terrific. All right. Awesome. Of course, I'm Universe Today on all the things. Lots of great interviews. So definitely come check out my YouTube channel, Twitter feed, newsletter. You should subscribe to my newsletter if you haven't already. It's super good. All right. Thank you, everyone, for joining us this week. Thanks to all my co-hosts. It's great to sort of see you all at the same time, arrayed. Thanks to our special guest. Thanks to Pamela for engineering this episode behind the scenes. Man, I know I go on and on about this every week, but I just love just hands-free hosting this show. It's so great.
You're getting spoiled.
I really am. Yeah. Well, I still have to engineer my own show on my own YouTube channel, so it keeps me in the game. But yeah, no, this is terrific to have Pamela staying on top of this from behind the scenes, and the rest of the team. So if you haven't already, go and participate. I guess CosmoQuest's Patreon, Astronomy Cast's Patreon. If you want to support the work that we're doing and pay for the salaries of everybody behind the scenes, go and support them. And thanks, of course, to everyone watching us on all the things. And a special thanks to Nancy Graziano for organizing everything. All right. Whoa, the screen just turned weird and green for me. I wonder if that's happening on the output. So I'm just going to call it right here. Thank you, everyone. And we'll see you all